Okay, so now we're going to actually implement some of the very basic components of a linked list. And to do this, I'm going to share my screen and go into NetBeans. And I'm going to make sure that I quickly bring up the chat so I can see if anybody's asking me questions. All right, so here we are in NetBeans. And I'm going to go ahead and make a class. We'll start completely from scratch on this one. And I'm going to call it my linked list class, just like the one I gave you. And I'm calling it this because I don't want to call it linked list, because Java already has a linked list class, and I don't want to name it the same thing as an existing class. I'm going to go ahead and cut that out right quick so I can have a little more space. And now I'm going to do a neat trick here. I'm going to define a node class. All right. I'm going to do this as what's called an inner class. In Java, you can actually define a class inside another class. You can't do this in C++, by the way, or some other programming languages, but in Java you can. So I'm going to take advantage of this capability, and I'm going to make a very lightweight class called node, and I'm going to make it private. I'm going to make it private inside class link, or my linked list class, so that nobody else can use it. This is a tool that my linked list class is going to use, and I don't want anybody else to have access to it. So I'm going to make it private class node. All right. And so now only methods inside the my linked list class can declare and use objects of class node. Inside class node, I'm going to store two things. I'm going to have an int called data. This is the part of the linked list that's storing the data part of the list. And then I'm going to have a node called next. Now this is a reference, which means it's the location of another object. So every node is going to store its own little integer, okay, I mean to disparage integers, its own integer, and its own next reference, so the location of the next item. And we're going to set that to null if there's nothing after it. Now in our class, we're going to create, a thing I just forgot. I'm going to make both of these public. Now, the reason I'm making these public is because I want my linked list class to be able to change them at will. So in my small inner class, class node, I am not going to encapsulate at all. This is a violation of the object-oriented principle of encapsulation, but I'm doing it for the benefit of the items, the methods that are inside my linked list class. The class itself is private, so only methods in my linked list class can access this class. So it is encapsulated at the linked list class level. It is simply not encapsulated at the node class level. So after this, I don't have to make getters and setters for these. I can just hit data and next and set them to whatever I want, but I can only do that from linked list methods. And so I want to also make a constructor like this, except I'm going to make a constructor that takes an int called value or data, right? And then this is what I want to do. I want data to be set equal to new data, right? And then I want next to be set equal to null. And by default, these items are already set to null. but I habitually set them to null whenever I want them to be set to null, so there is absolutely no mistake. In C++ and in C, these types of variables are not automatically set to null, so I have gotten in the habit of making sure I do that on my own. And so now what I've done here is just created a little class that has a constructor, and now inside my linked list class, I can make these nodes whenever I want. And that's why this class exists in this other class. This is why the node class exists in the my linked list class. And now right after this, I'm back in the linked list class. I want a private node reference, and I want to call it head. As I've mentioned in the other file, which you may have seen, this is the anchor point. For the whole list. Okay, and that's all I need. Now I do want to make a constructor for the my linked list class, so let me go ahead and do that. I didn't, I want to generate it, and this is all I'm going to do. Not head minus, head equals. This creates an empty list automatically. Now I want to get into methods where I'm actually doing something, and the first thing I'm going to do is insert at head. So in this case, I'm just going to insert something at the head of the list. So I almost went to the board. In order to do that, I need to be able to make sure that I'm thinking about this right. So I'm going to stop sharing right quick, and I'm going to talk from this angle. So here's the deal when I want to insert at the head of a list. All I want to do is to have a node in front of my first node. If the list is empty, then I will just insert the new node. If the list is not empty, then I've got to make sure that when I've done, my new element, my new node, is here. My head pointer is pointing at it, and its next is pointing there. I have to make sure that that is what my list looks like when I'm done inserting at the head of the list. This is the simplest and also most computationally efficient way to put something into a list, assuming it doesn't have a tail node, which we don't have. We'll talk about tail nodes later. So when I want to insert at the head of the list, then this is what I do. I'm going to say public, and you could argue that you would want to make sure that this worked, right? For example, you might want to make sure there's enough RAM or something. But realistically, this is always going to work. So I'm just going to say void, because if this doesn't work, then we have problems that this particular method is not responsible for. Running out of RAM is not our problem. Somebody's doing something somewhere else and running themselves out of RAM, so I'm not going to really care. And I'm just going to call this insert at head, and then I'm going to take some value to put there. All right. Now, oh, I need to share again. All right, so this is what I just said in code. Thanks for waving at me. Public void insert at head, taking the value. That's what I typed while you were just staring at my face. And so I don't need to necessarily return a bool like I did with the inserts and in this particular case, because there's no way for this to fail except running out of RAM. Now, here's the thing. I need to do this with a sequence of very discrete steps that are very critical. And it's critical that I do these in the right order. So step one, let me make these as comments. Step one, make a new node. All right. In order to insert an element into a linked list, it has to go into a node. So I need to make a new node. Fine. In order to make a new node, I need to hold it because it's an object. I could just say new node, right? And then put value there. This would create a new node, but then it would just sit there in RAM. It wouldn't be held in place. I could say, well, if I'm inserting a new node, let's point the head at it. Head equals new node. Fantastic. Now what I did was I pointed my head reference at a brand new node, and that brand new node's next is null, so I just lost the rest of the list. I don't know where it is. So I can't do this. What I need to do is I need to create a temporary reference to hold my new node in place while I link it into the linked list. So that's what I'm going to do. I'm going to say NodeTemp equals new node. I've created in this stack frame a node reference called temp. It's in the stack frame. It's going to exist only as long as this method is running. And what it's doing right now is it's storing the new node that I just put into RAM. So that's step one. Create a new node and hold it in place. I can spell step. Step two, I need to link the new node next. All right. So what this means is I set temp dot next equal to head. All right. What this does is it allows me to point the new node's next at the current head node. And by the way, if there is no current head node, it will simply be set to null, which is what I want it to be anyway, because if the list is empty and I'm inserting into it, then I want this node's next to be null because it's the end of the list as well as the start of the list. And then step three, point head at new node. I need to point the head reference at the new node because this new node is now the new head node. Well, that's real easy. I just say head equals temp, and that's it. So these three steps enable me to weave it in. Now, let me stop the share so I can talk again, and let's talk about why this works so well. First of all, I'm going to make a small change here. I noticed that this was a little bit high, so I'm going to erase it and move it just a little bit. So at this point, my head reference is looking at a node that is storing the number 4, and the number 4 is pointing to another node, and so on. But I don't care about any of the stuff outside of what the head is pointing at. That's the only thing that concerns me when I am inserting at the head of a list. So here's the steps that I just wrote. I'm going to draw them out. The very first thing I do is I create a temp reference, and I use it to create a new node that is set to null next. And then whatever value is, I'll just call that V. All right. So I've used a temporary node reference to point at a node that's brand new and its next reference is null. That's step one. Step two is I must link this reference to this node. I have to do that next. If I don't, I will lose the rest of my list, because if I set head to this node first, then the connection to that node is broken which means the connection to the whole rest of the list is then broken. So the next step is to set temp next equal to head. And now that I've got this node pointing, and now this node is anchoring the rest of the list, now I can set head equal to temp, and now the whole list is intact. The method ends, the stack frame goes away. When the stack frame goes away, temp goes away, and voila, my list has all of its items in it. And that's how you insert at the head. Does anybody have any questions? Or give me a thumbs up if you understand. Okay. So that's the inserted head. And as long as I do that, I could just pile nodes into this linked list as long as I have RAM. These lists can get massive, but then so can array lists. All you got to do is declare an array that's massive in size. But the difference here is these nodes will be all over the place potentially in RAM. Following them will be like following a spaghetti noodle. There's no way to find the 20th node. Now, do you see sort of why that is? You have to start at the head and move your way through the nodes in order to find any given node. Now, the next thing I want to talk about is size. In a linked list, you don't have to keep track of how big it is. In an array-based list, you absolutely have to. And here's why. In an array-based list, you have an array, and the array has a capacity. And the array is split up into two sections. Section 1 is the part of the array that is in the list. And section 2 is the part of the array that's left over that is not in the list. And to differentiate those two, you have a variable called size or length or whatever, right? That tells you how many of the elements in the array are in the list. If you don't have that integer, you can't tell where the list ends and the rest of the array begins. So it's critical to have an int telling you at what point in the array the list ends and the empty space begins. A linked list, they are not contiguous. So the thing that tells you when you're at the end of a linked list is the null pointer, right? So if you reach a node and that node's next is null, then you're at the end of the list and there is nothing beyond it. Okay? So we don't have to store how many things we have because we can always tell when we're at the end of the list. However, in order to figure out how many elements are in a list, we have to count them if we want to know. We can keep track when we insert, but we don't have to. So I'm going to show you how to count nodes. This is a very important method because it teaches you how to traverse a linked list. That word traverse is hugely important because you already know how to traverse an array, right? You traverse an array typically with a for loop, for int I equals 0, so long as I is less than array.length, I++. That's a traversal of an array, right? Traversing an array-based list is the same thing, except you don't put the length of the array, you put size. As long as you're below size, you traverse the list part of the array. Well, in a linked list, as long as the thing you're looking at exists, you're in the list. So what we're going to do is this. We're going to create a temp reference. and we're going to point it at head. All right. If head is null, then temp will be null. If head is not null, then temp will be pointing at a node. It will have to be pointing at a node if that's true. So once we have temp pointing at the head node, we will set up a while loop. And through every iteration of the while loop, we will do two things. We will count the node that we are pointing at, and then we'll move to the next node. And if that's not null, then we'll count that node and move to the next, and we will continue to do this. The moment we get to the last node and set temp equal to that node's next, temp will become null and we'll kick out of the loop and our count will be complete. So let's switch to the code and implement this. Let me do my share screen here. And now we're sharing again. Let me pop the chat back up. Okay. And so we'll make this public, not public, whatever. Still can't spell it. We're going to return an int, right? Because we're going to count how many there are. And we'll just call this size. This is a typical thing for lists. Arrays typically have length. So you have the length of the array. But lists often have size, which is how many elements are in the list. That's just sort of standard, but they're sort of interchangeable. Now, in order to calculate this, I'm going to have an int called count, and I'll set it to 0 because when we start, we have no nodes counted yet. And then I want a node reference. I'll call it temp, and I'll set it to head. A lot of people call these cur, C-U-R-R. That's a common name, or current node or something like that. I'll just call it temp. It doesn't really matter. And then what I want to do is I want to iterate through the list. Now, I'm going to choose a loop. If you remember early in the course, I told you how to choose loops. So in this situation, I do not know how many nodes there are. So I don't know how many times I'm going to iterate. Because I don't know, I shouldn't use a for loop. For loops are for when you do know. That leaves while and do while. So how do you choose between while and do while? Well, if that number that you don't know might be 0, then you should use a while loop. And that's true here. There might be no nodes, so I might not count at all. So I'm going to use a while loop. So while temp is not equal to null, so long as this is true, temp is looking at a node. Okay? So long as that's true, we know we've got a node. So since we know we got a node, we'll count it. And now we'll advance to the next node. Okay? And when we advance to the next node, we will set temp equal to the next reference, and eventually that will be null. When it's null, we have gone off the end of the list, and so we are done. At that point, we return count. Now, the nice thing about this is, if there are no nodes in the list, then head will be equal to null. If head is equal to null, then our while loop will not iterate at all, and so our count will be 0. And it will work in all other situations. Now, Any questions? Okay. I'm going to create a driver for this just to run some tests. Public static void main tab, my favorite thing. I'm going to create a scanner up here, like I always like to do. I like to create a keyboard scanner, make that private so I can use it here, and then I'll fix the imports to get that up and running. And so now I'm going to just add 5 nodes to this list. Just say enter 5 numbers, and then I will do this. Oh, first, I'm sitting here thinking, what's going wrong here? And of course, I haven't declared an object of my LinkedList class, silly me. Yeah, I'm already sick of typing that because that's a pain. Pop that in there, and now I can say my list dot, and I'll do insert at head. All right, and I'll do keyboard dot next int. All right, and I'll just be able to type those, and it's barking at me. Oh, of course, this has to be static. My mistake. And then after I'm done with that, I will S out the size. Okay, and it should just print how many I've typed. So let's run it and test it. So we'll enter 5 numbers, 4, say 8, 3, 87, and that, and it printed 5. So that was what it printed at the end. Run it again right quick just to show you that it did that. Okay, so that's good. It's counting. Let's do this. Let's right quick take this out, comment it out, and it should print 0. It's going to print the message first because I wasn't careful, but it just said enter 5 numbers, size 0. So I should have commented out the enter 5 numbers, but whatever. All right, are we okay with this? Everybody getting this? Okay. I'm going to stop the share. Well, first let me undo that. And I'm going to stop the share right quick. And I'll talk about the very next one that I want to do. And this is the last one I'm going to have time for today. But it is the print list. Now I'm going to print the list by doing the exact same trick I did when I counted. Except instead of counting, I'm going to print. That's it. So a lot of linked list methods traverse the list using this temporary node reference that moves through the list doing something when you want to add them together, when you want to do whatever, printing them. So that's what I'm going to do. Let me get back to the shared screen so I can make this, and we can move on then. Going to my linked list class, I'm going to do a print. This is a public method. I don't need to return anything because I'm just going to print it to the screen. Print list, right? And this is sort of unimaginative, but that's okay. It doesn't really matter. And I'm going to declare a node called temp, set it equal to head, right? This is established that I'm at the beginning of the list. And exactly like I did before, while temp is not equal to null, as long as it's not equal to null, it's pointing at a node. And if it's pointing at a node, I want to print it, right? And I don't want to print it, I want to print it on one line, a horizontal line. So I'm going to print temp dot data, right, plus a space, just to put a space in between them. And then the fun thing about this print list is that's it. Now that I've done that, oh, I'm sorry, I forgot silly me, I forgot one thing. I very clearly need to move temp equals to temp dot next to iterate through the list. Otherwise, I would just infinitely print the head node, which is amusing but incorrect. So the print list and the size are just straight traversals using while loops and temp references. And so when we do this, right before we print the size here, we can do mylist dot print list. And we could do that before or after. Let's actually do it after so we can see size 5 and then the thing. And now when we run this, we should be able to enter 5 numbers, right? 346, 73, 7, 3, and 8. And then they print. Notice that they print in reverse order in terms of how I type them. When you enter something into the head of the linked list, it becomes the first element in the list. So when you insert a bunch of elements at the beginning of the list, they will go into the list, and then if you print them from the head of the list down, they'll print in the reverse order that they were entered. So fun fact. Anyway, any questions about this method? Any questions about either of these 3 methods? If you understand them, give me a thumbs up. If you don't, then we'll talk. All right, so those 3 represent really simple methods. The remove at we don't really have time for because I know some of you have to go to class. So we'll call it a day, and on Wednesday I'll show you the remove at head, and then we'll talk about the insert at and the remove at, which are very complex by comparison. And we'll see how to build those. All right, everybody good? Then we're good.